So early in this unit, the only thing we've been talking about were exponential expressions, exponential functions. Let's recall what an exponential function is. An exponential function is a relation of the form f of x equals b to the x power. And there are restrictions on b. I'm getting tired. We don't need to write the restrictions. You know b has to be positive and not 1. Now notice what's going on in this equation. The input is the exponent, and the output is the actual answer, right? So this is what function notation says. X is the input, and f of x is the output. It's the y value. So an exponential function, it sort of puts the spotlight, the focus of the answer on the result that we get. So when we're working with equations like this, we are interested in the answers. So using exponential functions is sort of like answering these questions here. Question number 1. What power do we get when we raise 2 to the exponent of 1? Of course, the answer, everyone should know, is just 2. What if I asked you, what power do we get when we raise 2 to the exponent of 2? And of course, everyone knows that the answer should be 4. What if I asked you, what power do we get when we raise 2 to the exponent of 3? And of course, everyone should know is 8. You guys getting tired of writing all these long sentences? I sure am. So this is why we use, well, basically function notation. All of these questions here can be translated thusly. If f of x equals 2 to the x, then question number 1 becomes, what's f of 1? Question number 2 becomes, what's f of 2? And question 3 becomes, what's f of 3? So take your pick. Do you want to write out all of these long sentences? Or do you want to write this and then these 3 bits? So you can see how function notation can save a lot of headache and certainly our hand. Well, notice again the whole purpose of this function. We are inputting an exponent, and the main result, the thing that we're looking for, the output, is the actual answer. What if we were to merely change where the spotlight of the function is? What if I am not interested in the overall answer, but instead I'm interested in the exponent that we use? Well, recall that the idea of swapping the spotlight, swapping what the input and output is, that is simply an inverse. So instead of asking what power do we get, let's instead ask these questions, right? Question number, or letter A, so just to differentiate from 1, 2, and 3. What if I asked you, what exponent do I need on base 2 to get an answer of 2? In other words, 2 to the what power equals 2. Hopefully you guys understand that the answer is 1. What if, letter B, what if I asked you, what exponent do I need on base 2 to get an answer of 4? In other words, 2 to the what power gives me 4? Of course, you guys should know that the answer is 2. And you guys can probably guess what my last question I'm going to ask you. What exponent do I need on base 2 to get an answer of 8? And of course, I hope you guys know that the answer is 3. So again, this was a pain in the butt for me to write out all these sentences. You can tell that my handwriting gets sloppy when I'm rushing. It gets really tedious to write out all these questions by hand. So we can use function notations to translate these questions. Now remember that we created these questions by swapping the spotlight. Instead of focusing on what power or what answer I need for a given exponent, I'm asking what exponent do I need for a given answer. This idea of the inverse of an exponential function, we just give it a fancy new name called a logarithm, right? So the idea of the inverse of the exponential function we simply call it a logarithm, right? Now, even then, mathematicians, we are sort of lazy. Logarithm is a pretty long word. We just abbreviate it as log. So, question A becomes, instead of writing out this long sentence, what exponent do I need, blah, 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 that's pain in the hand, I can simply write log base 2 of 8 equals question mark. This symbol here, this notation, says everything in this sentence. So you can basically translate in your mind, whenever you see a log, it's the question, what exponent? This says, an answer of 2, my bad, an answer of 2. This basically says, what exponent on base 2 gives me an answer of 2? Question B becomes log base 2 of 4 equals question mark. This question here is the same thing as this notation. This literally says, if I were to read this guy here, down here, if I were to read him, this really says, what exponent on base 2 gives me an answer of 4? And lastly, I can translate letter C. This becomes log base 2 of 8 equals question mark. So in general, the question, what exponent do I need? That's all it is a log. And that's it. That's the big mystery. You know, logs look like high-level fancy schmancy math, but the idea is rather simple. A logarithm is nothing more than an exponent. So if you want to link words together, logarithm should be synonymous in your mind to exponent. Of course, we really haven't been doing anything fancy, formal, and rigorous, so let's go ahead, for the sake of our notes, put down the textbook, high-level college definition of a logarithm, right? Definition of the logarithmic function. Here's the definition. Let B be a positive number with B not equaling 1, because again, it's really boring if the base is 1. Then the logarithmic function with base B. That phrase there is how we pronounce it. Oh, it's the logarithmic function of base B. In a pinch, you can sort of get rid of the word function, so you can just say the log with base B or the log of base B. the logarithmic function of base b, denoted by log base b, so that's how you write it, is defined by this relationship. Whenever you have log base b of something, that equals another number, right? So again, you can see that the input is inside the log, so a log should always spit out something. But what's so special about that something? This something here is going to be the exponent on this base that gives you this answer. Or in other words, b to the y power equals x. So the left is 100% the same as the right. So if you want to know where the pieces are, whatever the logarithmic base is, that will always be the exponential base. Whatever the log equals, that will be the exponent, because a log is just nothing more than an exponent. And the inside of a log, the argument of the log, is the power of the exponent. So in other words, log base b of x is the exponent to which we need to put on base b to get the answer x. Now, I did say that both of these guys are equivalent. They are equivalent statements, but clearly one looks different than the other. The left expression uses a log, so we call this logarithmic form. The right-hand side uses exponents, so we call it exponential form. And one of the things that you're going to be asked to do on the practice and be comfortable with is convert to and from each form. And all it is understanding the relationship. Basically, these types of questions, they are testing your reading comprehension. Do you really, truly understand what a log means? So let's write down a true statement involving exponents. So what is true? Right? Convert into logarithmic form. What is a true statement? Well, I know it's true that 2 to the 5th power equals 32. That's a true statement. If I want to convert this into logarithmic form, I need to focus on the exponent, because that is what a log is. A log focuses on the exponent. So what's the exponent in this expression? Well, it's 5. So I can say 5 is the exponent, and then in math, exponent is log. 5 is the exponent on the base of 2 that gives you an answer of 32. This is the logarithmic form of that. Let's do another example. I'm just going to write down a true statement. I know 3 to the 4th power is 81. So the logarithmic form is 4 is the exponent on base 3 that gives me an answer of 81. It doesn't have to be whole numbers. It could be fractions too. Remember your properties of exponents. I know that 4 to the negative 2 power is 1/16. We can convert that to logarithmic form. I can say that negative 2 is the exponent on base 4 that gives me an answer of 1/16. I believe on the practice, they're going to have you be comfortable going forwards and backwards. So basically, if I give you, the idea is one objective for today, if I give you exponential form, you should be able to give me log form and vice versa. If I start off with log form, you should be comfortable with transforming it into exponential form. Just give it a practice, and if you have any trouble, please ask questions. If you truly understand what a log means, you can evaluate it, because that's all logs are. Logs are answering the question, what power, right? So I guess I should write the idea first before jumping into the examples. To evaluate logs is to answer the question, what power? For example, if I ask you to evaluate log base 4 of 64, this is asking what exponent on base, what is the base in this case? Well, we can clearly see it's the small number, 4. What exponent on base 4 gives me, what is the argument? 64. So that's the question that you're answering. So I hate to say this, but in order to be good at evaluating logs, we have to know our exponents, right? We just have to know that 4 cubed gives me 64. And of course, if you are not so good with your exponents, well, you can sort of guess and check with a calculator. But that's how you evaluate, right? You just have to know your powers. I do have some hints and tidbits for you. What if they use radicals? Say, for example, log base 5 of square root of 5. We need to remember that radicals are nothing more than fractional exponents. So this is the same thing as log base 5 of 5 to the 1/2 power. So this should be a fairly trivial question. This is basically asking you, gee, what exponent do I need to put on base 5 to give you an answer of 5 to the 1/2 power? Well, clearly, take a look at it. What exponent do I need to put on the 5 to give me 5 to the 1/2 power? Well, what exponent is there? Oh, it's clearly 1/2. Now, I answer this question using properties of exponents. Knowing about properties of exponents will be very, very helpful, especially when you have problems like this. Notice how the base is a whole number, but the argument is a fraction. Well, in terms of exponents, because that's all logs are, the only way you can transform a whole number to a fraction, or vice versa, is with negative exponents. So I may not know what the answer is, but I do know that the answer is negative. And of course, once I take care of that, you just look at the numbers. You basically ignore the fraction, 5 and 5. Well, what exponent on 5 gives you a 5? That has to be 1. What other tidbits? Oh, if you go from a big number to a small number, right? Log base of 81 of 3. What's log base 81 of 3? Anytime you go from a small number or a big number to a small number, like with exponents, exponents typically make things bigger. 2 to the 5th power gives you a big number. 4 to the 8th power gives you a big number. 4 squared gives you a bigger number. So typically with exponents, they get big numbers. The only time you go from big to small is with radicals. And radicals are nothing more than fractional exponents. So because I'm going from big to small, I know that my answer will be a fraction. And then once I figure out it's a fraction, I just have to figure out the power. What's the relationship in terms of exponents connects 3 with 81? And I hope everyone knows that 3 to the 4th power is 81. So it has to be 1/4. Again, guys, when it comes to this situation, it just takes knowledge on your powers. It's one of those math topics where you either get it or you don't get it because you need to know your exponents. So this would really test your exponent skills. To help with the evaluations, there are some helpful hints and properties. Here's the first helpful hint. Whenever your argument is 1, it doesn't matter what the base is. The base could be a fraction. The base could be a big whole number. If your argument is 1, your answer is always 0. Why? Well, because properties of exponents. A log is an exponent. And what is the only exponent that gives you an answer of 1? 0. Another helpful hint, since logs and exponentials are inverses of each other, whenever you have a log base with an exponential base that are the same, they will always cancel out. So if this was log base 5 of 5, log base 7 of 7, log base 1/2 of 1/2, they will always cancel out to 1. Why? Because 1 is the only exponent that will give you the same thing out. And by extension, we can do function composition. If I have a log base b, and I stick an exponential expression in there, These guys sort of cancels out, giving you what's left over x. And it works the other way. If I have an exponential base of b, and in the exponent is log base b, because exponential functions and log functions are inverses, it's sort of as if these guys cancel out, and it gives you x. So these properties and hints might help you guys evaluate, quote, harder looking problems. So for example, if I gave you log base 3 of 3 to the 7th power, I shouldn't have to do a lot of thinking. I should know that, hey, log base 3 and 3, they match, so they cancel out. That gives me 7. Right? 7 to the log base 7 of 18. Hey, exponential base of 7. Log base of 7, they're the same, so they will cancel out and gives you 18. I want to finish off by sort of giving you some special notations and definitions. Logarithms, you guys can see, can take on any base as long as it's not negative or 0 or 1. However, the two most frequently used bases are base 10 and base e. So if the base is a 10 or base is e, since we use them so much, we give them special names. So first definition, we call a logarithm the common log. That's the official name of it, common logarithm. I guess I should not abbreviate, common logarithm, if it has a base of 10. If you do have a common log, we do not write the base subscript. In other words, log base 10, if your base is 10, we don't even bother writing the 10 there. Right? So if you ever see a log without a little base, you can safely assume it is always 10. Second definition, we call a logarithm the natural log if it has a base of Euler's number e. His special symbol, if your base is ever e, we use ln. ln stands for natural log. Right? Now, I guess if you twisted my arm and asked me, hey, Mr. Vo, is it wrong if we write log base 10? Is it wrong if we write log base e? Technically, no, it is not wrong, but I promise you every single math professor you will encounter will use the common log x or the ln of x. So please get used to those notations there. So it's just shorthand notations, guys. All the logic is still the same, right? If I asked you to evaluate log of 10,000, this is still asking, even though you don't see it, still asking you what exponent on base 10 gives you 10,000. And if we know our exponents of base 10, that's going to give you a 4. If I give you e raised to the log n of something crazy like 1 over pi, well, you just have to remember that ln has a base e down there, even though you don't see it. Hey, base e, they will cancel out. 1 over pi should be your answer.